Let's take a look at this example. A person standing on a low friction cart walks across the cart to the other side. In this first image, the upper image, we see the person standing on the right end of the cart. The person has a center of mass, probably not too far off from where their belly button is located. I'm going to mark it here in green underneath the person. All I care about is the horizontal location of the center of mass. The cart has a center of mass. And if our cart is uniform density, its center of mass is at its center. So the system, the person plus cart system, has a center of mass. If the cart and the person are about the same mass, the center of mass of the system will be halfway between them. In the next image, you see the person starts to walk to the left across the cart. And as the person starts to move to the left, what does their foot do? It pushes against the ground, causing the person to go to the left. And what's that force going to do to the cart? It's going to cause the cart to move to the right. So as the person moves to the left, walking across the cart is moving to the right. And in this middle image, we've captured the person halfway across the cart. So where's the person's center of mass? It's underneath the person. And where's the cart's center of mass? It's at the center of the cart. And where's the center of mass of the system? It's right there. And our person continues to move in this direction, and the cart continues to move in that direction until the person reaches the end of the cart and they stop. And of course, that's going to cause our cart to stop. So everything is at rest now. The horizontal location of the person's center of mass is right under where they're standing. Our cart's center of mass is at its center because it's uniform density. And the center of mass of our system, the cart plus the person, is halfway between them if they have the same mass. And what you might notice here is that as long as this is an isolated system, if no external forces are reaching in, influencing our system, the center of mass motion cannot change. In this case, the center of mass was stationary to begin with. It was at rest. So it had to stay at rest in the same place the whole time. Internal forces, the person pushing on the cart pushing on the person, internal forces cannot change the motion of the system. An external force has to reach in to cause a change to the motion of the system, to cause the center of mass to change its motion. So if I draw a line down here at this fixed point in space, the center of mass never moved from that line. It started out there. As the person moved in one direction, the cart moved in the other direction. What happened to the center of mass? It stayed right where it was. And the same would be true if the center of mass had been moving with some velocity. If the center of mass was moving with velocity v cm, as the person moved in one direction, the cart would move in the other direction to keep the center of mass of the system moving with the same speed in the same direction. No changes there. There has to be an external force, something reaching into the system from outside to change the motion of the center of mass. This is why center of mass shows up in most physics textbooks in the momentum chapter. This is the same condition we have for momentum conservation. There has to be no external force acting on our system for momentum to be conserved. So if we put ourselves at the location of the center of mass, it's a little easier to solve momentum problems. But the trade-off is you have to do some velocity transformations to get all the velocities in the center of mass frame of reference. But center of mass comes in handy for other types of problems also. So let's take a look at how we calculate center of mass, and we're going to start out with point objects. In this problem, we're trying to find the center of mass of these 4 point objects. The masses are given, the locations are given. Let's find the center of mass. Here's our equation to find the center of mass. It's basically a weighted average. We're multiplying the mass by its x coordinate and then adding those all up and dividing by the total mass. So in this case, our x center of mass is going to be m1 times its location, x1, plus m2, x2, and all the way up to x4. And we'll divide by the total mass. So m1 is 1 kilogram, and its location is -1 meters on the x-axis. m2 is located at 0. m3 is located at x equals 3 meters, and m4 is at 0. So the x location of the center of mass is at 4/5 of a meter, or 0.8 meters. So somewhere on this line is the x center of mass location. In other words, if these 4 point masses were connected by some kind of a massless structure, massless rods, where would I balance it? Where would I be able to balance the object? Somewhere on this red line, because that's the x location of the center of mass. Now I have to find the y location of the center of mass, and then I'll know the exact center of mass location. We use the exact same equation, only now we make these x's y's. So the y center of mass location is going to be the mass 1 multiplied by its y coordinate, plus mass 2 times its y coordinate, etc. So I'm just plugging in the masses and their y coordinates. When I get to the 4th mass, I have to plug in its y coordinate, which is -1 meter. So the y coordinate of the center of mass is 0. If I look back at my coordinate system, I see somewhere on this green line is the y center of mass. And where these two intersect, that's my center of mass of the system. So the center of mass is equal to 0.8 meters, 0. One interesting thing about this is that it does not depend on the coordinate system. If I pick a completely different coordinate system, I'll use green, and I'll call this x prime, and I'll call this y prime. So in the x prime, y prime coordinate system, I could go back and do this exact same calculation. Only my x coordinate is not going to be 0.8 meters. It's going to be 3.8 meters. It's going to be where this red line intersects my x prime axis. It's going to be 3.8 meters because m1 is now at location x prime equals 2. Instead of being at -1, it's at 2. And m2 is now has an x coordinate of 3 in this new coordinate system. So if I plug in all the new x coordinates, I get 3.8 meters for my center of mass x location. And I get, for my y location, I'd get 2. So in this new coordinate system, the center of mass is going to be 3.8 meters, 2 meters. But it's in the exact same location relative to the masses. So if I wanted to balance this on my finger, where would I put my finger? In both cases, I'd put my finger on that red X to balance this structure.